In this video lecture, we discuss each individual material composing the module. We address material functionality together with potential failure modes that can lead to degradation of a PV module. This last aspect is crucial because during its operation, a PV module is simultaneously exposed to environmental stress like sunlight, temperature, moisture, and mechanical loads. These factors often lead to a gradual degradation of the module performance, which will be discussed in the following lectures. Now, we look at the standard module architecture as we discussed in the previous lecture. The PV module includes a frame, glass, encapsulant, solar cells and internal circuits, a backsheet, a junction box, and output cables. Let's first talk about the frame. Normally, an aluminum frame is utilized. The main functionality of it is to protect the edge of the glass and provide module mounting points. Besides, aluminum frame has good conductive properties and can be used as lightning protection during thunderstorms. Moreover, the strength of aluminum frame is high, which could provide a stable and a reliable support to the module. However, in practical use, frames can become loosened, deformed, and corroded over time. This increases the risk of module damage and in turn can contribute to degradation of the module performance. The glass acts as a module front cover. Low iron soda lime glass is commonly used. It is highly transparent and it provides electrical insulation and prevents moisture and gas from entering the module. In addition, PV glass is sometimes coated with anti-reflection or anti-soiling layers to improve the overall module performance, so increase energy output. Failure modes of glass can be breakage, soiling, or abrasion. Glass breakage is found to account for up to a third of module failures, which may occur during transportation, installation, and operation of PV module. Solar cells are in direct contact with elastomeric materials called encapsulants. The widely used encapsulant material is ethylene vinyl acetate, or EVA for short. They act as adhesives, sealants, and optical coupler in solar panel. The main failure mode of PV encapsulants include discoloration and delamination. On the bottom right, one can see examples of encapsulants discoloration, forming a brownish haze due to UV exposure. An example of encapsulant delamination is visible at the edge of the silicon wafer, turning gray in the right figure, and it can be caused by water ingress. Apart from that, the interaction of EVA with water can lead to acetic acid formation, which can further degrade the module performance. We now look at the core of the PV module, the solar cells. They are the active components that generate output power. Various failure modes exist. The first one is cell cracking. The appearance of cell cracks can be detected by electroluminescence measurements, or EL. On the bottom right, we show an EL image of a module with one cracked cell in multiple locations. Although you always need to prevent cell cracking, it does not automatically result in lower module output power. Namely, the different cracked parts of a cell can operate in parallel and deliver the same output a cell that is not broken. A second failure mode is hotspots. Hotspots are areas that reach elevated temperature caused by high reverse currents in local shunt paths. They can usually occur in areas with partial shading, for example, material dropped on the module or by soiling. Hotspots can potentially cause severe module degradation and accelerate the formation and propagation of other failure mechanisms. The bottom right figure shows an infrared thermography image with two hotspots in a PV module. The next failure mode is called potential induced degradation, or PID for short. It's mainly caused by the different potentials between module frame and solar cell of a PV system under operation. Since modules in a system are connected in series, the voltage in the solar cell matrix inside module can easily add up to very high values, even beyond 1000 volts. A diagram of PID process is shown here. The high system voltage creates an electric field between the grounded PV module frame and the solar cell matrix, causing alkali methyl ions to diffuse towards and inside the solar cell, resulting in severe power losses, which will be discussed in a later video. Strategies to mitigate PID phenomena are discussed in the listed literature. The last important failure mode of solar cell is light and elevated temperature induced degradation, or LETID for short. The bottom right figure shows EL image of a PV module before and after light and temperature induced degradation. Before LEITD, solar cells shows regular luminescence intensities, while after LETID, a disordered chest pattern can be observed. More details about light and temperature-induced degradation will be given in the next lecture. Next, we look at the solar cell metallization and interconnection wiring that constitute the internal electric circuits of a laminated module. For the traditional silicon PV module, the failure mode of internal circuit mainly include corrosion, which results in the discoloration of the string interconnected ribbon, and fatigue cracking, such as broken interconnected ribbon between cells. Both modes are visible in the images at the bottom of the slide. Moving to the back sheet, that has function to provide electrical insulation and environmental protection to the PV module. The failure mode can be discoloration, cracking, or delamination, which can be seen from the figures on the bottom right, respectively. Junction box is used to protect the connections of strings, external wiring, and bypass diodes. Its failure mode can be detachment from the module backsheet, poorly sealed or closed box, corrosion, or arcing. While the bypass diodes are protective components intended to minimize module losses during reverse bias operation by providing a path for the current of good cells to bypass bad cells. The main failure mode of bypass diodes include arcing, electrostatic discharge, and thermal runaway. To recap, in this lecture, we elaborated on the functionality of different PV components, including the frame, glass, the encapsulant, solar cell, internal circuit, the backsheet, the junction box, and the bypass diodes. Different components can have different failure modes in practical operation, causing degradation of module performance. Engineers should minimize and prevent degradation as much as possible, and quantitatively predict degradation phenomena that cannot be eliminated. This will enable a more accurate estimation of the expected service lifetime of a module and its electricity yield. For this purpose, accelerated lifetime testing will be introduced in the following lecture, and the degradation mechanisms will be further discussed in week 4 of this course.